Oops. Okay, why don't we get started here? So, I'm still waiting on getting some tests back, but we're working on it. Let's see. Homeworks 1 through 5 should be graded. Do check GLOOKUP and tell me if you see any anomalies. And yes, okay. So I thought I'd do a couple of things today. So first of all, there were a couple of slides to finish up from last time. Then I wanted to do a little bit of discussion of the project because it appears, gratifyingly, that some of you have actually started on it, which is good, even if you are a couple of weeks late starting on it. I don't know, you guys are losing your sense of humor, that's all I can say. Okay, fine. I wonder why. Okay. So, fine. So, first of all, questions, administrative or otherwise? Good. Okay. A quick note. One of the problems that I noticed with Piazza, and I'm not exactly sure what the right way is for me to correct for it, is that so unanswered questions show up for me as nice big red questions, and that's a flag. But then, of course, sometimes we get a student answer, and I'm not sure that I always get the things properly reviewed. So if you find that something isn't, if you find some answer that's unsatisfactory, always do a little unresolved follow-up so that I can notice that there's something left. Just remember that. Otherwise, things might get lost. Okay, so, and if your question is something's wrong in your program, or you think something is wrong in the framework, or you think something is wrong in the supporting software, always do a bug submit with these things. Don't just post them, because then they will probably never get fixed, and also, of course, you will not have supplied enough information. So, for both those reasons, please use it freely. All right, so we were doing this example, and I've done some corrections since last time. First of all, let's just review what this is from. So using these rules for some language, let's just make this visible here. Using these rules, which cover head, tail, integer literals, if, and so forth, we're going to, for a language without subtyping, without object orientation for the moment, we're going to type this and infer the type of this little expression here as best we can, and infer the types of all, and in particular, and also to infer the types of all the variables like P and L and F that are used within it. So again, the idea will be that we start out by saying, well, P, L, and F are the unknowns here, and they have some unknown type. So we'll just assign variables to them, type variables, and then we will apply the rules from the language, which give two things. They tell what the type of an expression is, and they generate an extra few side conditions or equations that must be satisfied in order for the thing to be correct and to have that type. So here we go. First of all, we look down and we do this bottom up, and we see that there's a PL. I think we did this last time. We see there's a PL, and if you consult back to the call rule, you'll see that this means that P has to match some function type, A0 to A1. L has to match the type of the the type of L has to match the argument type of the function, and the type of the whole thing will be the return type of the function, A1, or the codomain of the function. So the result of this is that we've introduced two equations. P goes to A naught A1, and L goes to A naught, or L equals A naught. We've introduced those equations relating the types of everything. And we continue in this fashion. So the head rule tells us that if you've got head of L, if you see an expression head of L, then L has to be of some list type, let's call it A2 list, and the type of the whole thing will be, A2. In other words, the type of object that the list is. And now we come to the interesting part where you have f applied to a two-argument function. All right? So f applied to the outer argument. So we know what the. All right. So that tells us that f has to be some function type, and it tells us that the type of the first argument, that is, which we know to be tic init, has to be equal to the argument type, and the type of the whole thing, f of init, is equal to A4. Now, it's just f init. Just f init because we're using this currying thing. That is, a function that has multiple arguments is a function that returns functions. So, fine. So far, so good. So, now, at this point, we have f init applied to head. In other words, we have another call. So we do that, we exercise this other call, and we see that, well, that means that the type of f init has to be, or the type of f init, which is this new type variable, A4, that we invented for the purpose, has to be itself a function type, right here, and it's the type of its first argument, which is to say head of L, and that's A2, we determine that up here, that has to be equal to its argument type, and the type of the whole thing will be its return type. Okay, well that's good. Now the if statement then tells us that the type of this thing up here, P of L, which we've determined to be A1, that has to be bool. It tells us that the init type, and it also tells us that the init type, that the then part and the else part of this if have to be some type that's the same. It's the same on both sides. So we invent a new thing, A7, and we say that both init and A6 have to be equal to A7. All right, that's fine. And that the result of the whole thing, the if as a whole, has type A7, fine. And now we come down to this thing below where because we have a plus rule, a plus, and plus takes integer operands, that tells us that A7, the type of the if, has to be int. And so that's it. All right. So those are all the equations. It gives us this bunch of equations, as you see here. And if we just take them in you can do them in any order. We might as well do them top to bottom. If you take these equations and perform unification on each pair, on each equation, one at a time, on the two sides of each equation, just unify them. And instead of reinitializing with fresh variables each time, just keep those bindings around as they are produced. Then you see this process. Namely, we learn very quickly, for example, that A2, that A naught, the argument type of P, has to be type A2 list. Right? And because L is A0 and A0 is the type A2 list. When we get down to, and finally when we get down to the end there, when we get down to the if statement, we link up a whole bunch of types with A7, and then we link A7 to int. And the final result is what you see down there below, I believe, anyway, that there is some unknown type, namely the type of the argument list, and the function the expression as a whole is integer valued, and the initial value, the init value itself, is int. So this is an interesting little exercise for a simple expression. It gets more complicated, obviously, when you get more complicated expressions. And this tells you, of course, that you want this to be done for you automatically, because if a relatively simple expression like this produces all these equations, then life will get really tough in a real program. Well, that's what this particular language's compiler, the ML compiler, actually does, and it's interesting. It's a style of programming. You get used to it eventually, and it has many proponents. At least when you get some of the successors. Now it's mostly successors to ML that seem to get used, such as, for example, OCaml, which is an object-oriented language. Haskell, which is sort of the latest variant of ML. These all use this type inference stuff in various forms and various elaborations, and I find it rather refreshing, actually, because unfortunately most of the type systems we use in other languages are not quite clean enough to do this in any nice way. But it's good to see. Yes. Right. Why do the two have to be the same type? Why are they both 8-7? Well, they both have to be the same type. I mean, I could have actually, you're right, we could have expressed this differently. We could simply have said that the side condition is that the type of the then is equal to the type of the else. That also works. I was just, suppose that I have an if statement. First of all, remember this is an object-oriented language. This is a non-object-oriented language. We're talking about language without subtyping. So suppose I had an if statement that said if condition then hello else 5 v. What is the type of that? What type of value does that return? Is it okay to add 3 to it? Well, not if. Apparently, that would mean that you have to check at runtime to see what its type is, and the whole name of the game here is static type determination. In other words, determining at compilation time whether a program's types are all matched up properly, rather than execution time. Now, in our project, we are we're sort of in backward compatibility heck, in that in order to allow some ordinary Python programs to actually run, since ordinary Python programs don't have any type attributions, I've sort of kludged and allowed a certain amount of dynamic type checking. But at least the places where it's necessary are well defined by the semantics. Okay, so that's type inference, an example of type inference, and I think it's a kind of a fun topic, and it's something that you will occasionally, I think you will occasionally see if you get serious enough about programming languages. All right, so much for this. This sort of wraps up all that we're going to say this year about types. And the next topic will be the last section, the last segment of the compiler, the runtime system and its and code generation. But before I do that, I wanted to say a few things about the project, a few comments about the project. I'm going to start with. I think what I'm going to do is make a regular segment of these lectures be a discussion of actual code segments from real students' programs, so that I can head off certain tendencies that we pick up as we observe these things. This is another reason, by the way, why bug submits are useful. They provide me with fodder. and I will try to eliminate. You will see the ... there, the ... AST in the fourth line or so. That's me eliminating identifying information from this thing. So there are a couple of things. These are some actual excerpts from bug submits from Project 2. And they illustrate a couple of things that in this particular case, these are mostly negative lessons, but I hope that in the future I'll see some positive things as well. And there are some positive things here too. So this first example, this is mostly a formatting. This is a formatting issue. You'll notice that it's not just the large font that I have to use to make things visible. That first line of the comment is 116 characters long. This is excessive. I suggest that you strive to keep your lines much shorter than that for readability purposes. I mean, even if you've got a screen that's wide enough, and I think maybe these people are showing off the wideness of the screens that they have at home. Just because a screen is that wide doesn't mean that your eye is comfortable with it. It's nicer if you can just sort of take the whole line at one fell swoop, with one saccade, as they say. So I usually try to keep things. I get nervous when things get beyond 72 characters, but of course that's because I'm a really old fart who used to work with punch cards, but still, actually, by happenstance, it happens to be a good general limit. So when things get up to 72 characters, it's time to start thinking about breaking the line into smaller segments. So that's one small thing. Now, the comment next line is 116 characters is my comment. You'll notice that we have a mixture of two different commenting styles here, the / and the / a personal indulgence, okay, a personal thing. It's purely personal with me. Don't expect to see others with this. I hate / comments. All right, it's an aesthetic thing, you know. I mean, you already have / Why do you need another comment style? That's the big thing. And if you're going to choose a character to use as a up to end of line comment, / was an ugly looking choice. Not to mention the fact that I don't know if the fact that it appears in certain URLs is significant or not, but it certainly wasn't at the time C++ was invented. In any case, I would appreciate it if you avoided those things, except for little segments of code that are meant to be meta comments for the reader, as in this case here, where I inserted that comment to explain what was going on here. All right, so otherwise, actually, this fragment is not so bad because it does illustrate one thing that's good. You have a field here, op, and you actually have a comment on it so that we know what it is, and that's probably good. On the other hand, you'll notice that we have this a rather complex comment. So if the operator is this, then it's such and such, and so forth. That's maybe getting. One begins to feel slightly nervous when things get that complicated. But let's go on. Now, this next example is, I think, typical of the kind of thing that you see a lot of if you're in my position. So, first of all, formatting. What's the matter? The space bar on your computer broken? I mean, what is this? What is this if parenthesis thing? I mean, I understand not everybody wants to use the GNU convention of having a space before the parenthesis in a call, which is a convention that I've adopted simply because I maintain some GNU code and or help maintain, it's always communal effort, help maintain some GNU code, so I'm sort of sensitized to this. But that's fine. And after all, getting rid of the space in front of the parenthesis is consistent with Python usage in the case of a call. But in an if, I mean, really, gosh, guys, come on. So if space child equals 0, let's see, is there an example of, oh yes, if parent name equals assign parenthesis space brace, I mean, or brace on the next line, whichever style you want. Please, I mean, gosh, I can't read this. It interferes with my astigmatism, no end. All right, so that's one thing. Another thing is that if we look through this, we notice that there's a lot of repetition, very repetitive code that's fairly complex. You know, AST node of make tree of AST node make token. I mean, that pattern, that's a pattern for making a new kind of tree. And it just cries out for a function, a nice small function, like, for example, an example in the framework I gave you, I think it's called makeID. It just calls out for a nice, simple function that will do that for you. And in this particular case, you look through the framework, you find there is such a function, although it's used just in the parser, and an obvious step would therefore be make it globally available and use it as a general utility. So whenever you see repetition, either at that level or there's a good deal of repetition here, it's time to think refactoring. That's the general term for taking code out and turning it into and abstracting it into some sort of function, so that abstracting pieces of a program into functions so as to make the program clearer and to make that fragment of code easily reused. Now, there's another thing about this code segment which is also quite common. I mean, the interesting thing about this is that this is not an egregiously bad example. I mean, every single year I see code that looks exactly like this. Now, I don't think it's plagiarism, because the code is all different. But at every single year I see people who crowd everything together like this, who make this next error as well. And it's very interesting. I don't know. One of these days I'll figure out what is so attractive to people about these particular problems. Now, this other thing is, you'll notice what's going on here. If my name equals subscription, if parent name equals assign. Now, if you are familiar with the project at all, as I hope you are, you'll recognize these terms. These are obviously types of nodes that he's talking about here, or that they're talking about here. If child equals 0, that's child number, presumably. That means that basically you're doing, this if statement is doing a type test, a test of the type of node, in effect. And it's conditional code based on that type. That is not how you do things in an object-oriented language. Instead, what you do is you think virtual method, think instance method. Right? That is to say, if this piece of code is supposed to behave differently with different types, then what that cries out for another kind of refactoring, a refactoring into virtual methods. So the action that depends on the type of that node should be a method that is different for each different type of node. And so that you just call this thing and get the right result. Now, in this particular case, we have, so there would be code for the subscription node. I don't know what this particular segment of code is supposed to do, but you figure out what generically is the thing that this code is doing, and that suggests the name of the virtual method that you're going to introduce. Up in AST nodes, you give some default definition of this virtual method, which might be either unimplemented, meaning that it's excuse me, it makes sense only in certain nodes, or it might be do nothing or return something random, as the case may be. And then in nodes where there's some special meaning, you do the right thing. Now, a very common pattern by the way, a very common pattern in this project will probably be the virtual method whose implementation consists of, for each of my children, recursively call me. And you'll see there are lots of applications for that. All right, now going back to this case, we see another problem here. You see, if parent name equals assign. Now, what I assume this means is that he's doing different things depending on what kind of node he's a part of, what kind of node his parent is. So if I am the left side of an assignment, I think this may have to do with assignment, yes. If I am the target of an assignment, then I behave in this way. If I am something else, then I behave this other way. Well, this is very dangerous because from conceptually speaking, you're not supposed to be in charge of the people above you in general. You're not supposed to know about them. Your parents probably would not welcome intimate knowledge on your part of certain things from their past. So, sort of methodologically, it's not a good idea. So, how would you? I mean, how do we rewrite this so that we don't have to ask what our parent type is? What would you do? Any suggestions? Yeah.
Do you have a virtual function that does it for you, depending on what type it is?
I'm sure. Where is this virtual function called exactly?
By the parent node.
It's called by the parent node, and how does this particular piece of code get rewritten then?
Move that code to the parent node, and the parent node looks at its children and decides what to do with children.
Yeah, so in other words, what this is telling us is that this code does completely different things depending on what the parent is, which means that this code really represents two different or several different virtual methods within the same node, within the same class. So it represents a what do I do if I'm on the left side method, and that is if I'm being assigned to method, and a what do I do if I'm providing a value method, or in the terminology used in C, L value side and then R value side. So these are two different methods that should be split up so that the code that happens when you're when you're being assigned to is different from is a different method with a different name from the code that's used when you're providing a value. So that means that there's a good deal of factoring here. We want to, first of all, break this thing into a virtual method that depends on with one name that depends on the type of the node that we're in, and we also want to break it into multiple virtual methods depending on the role that this node is being asked to play, so that you don't have this complex decision at each point. This will result in smaller methods all around and more easily understood methods all around. All right, so as a general rule, in 61B, if anyone's taken 61B with me, although it's been a while, I say at some point, I introduce the instance of operator, and I say, this operator is here so that we can take off points if you use it. You generally don't want to use that. And Strostrup has said something like this when he explains why he doesn't have an instance of, or didn't originally put an instance of operator into C++, and why he's eventually added it only in the rather clumsy form of the dynamic cast thing. He says, well, because you're not supposed to do it that way. That's why. So that's sort of the takeaway here. Okay, so these are two things. I think that's enough for one day. Because we have plenty of time we have a certain amount of time before to display this in the future, so I'll do that. Okay, let's see. Good. Why don't we take, at this point, let's take a brief break and then I'll consider, oh, but I'm sorry, did this raise any questions, first of all? What else will, along the lines of what else will upset you, that sort of thing. Yeah?
What about pound-defined macros?
Pound-defined macros. I actually am a fan of the tasteful use of macros. So the question is, what about macros? However, the tasteful use of macros, notice the word tasteful. So the macros used to be used for defining symbolic constants. In C++, that's generally unnecessary, and you should use enumerals, enumerated types, or const declarations instead. And they're also used for they've also been used for inline functions, that is, functions that are expanded that instead of calling the function, you actually expand it where it stands. This is no longer necessary in C++ because it has an inline declaration, and you can and that has the advantage that there are certain dangers to doing this with macros, having to do with name collisions and so forth. So it's better to use the inline directive. But there are two applications, or a couple of applications of pound-defined macros that are useful. One of them is in defining new control structures. So, for example, the thing that iterates over children, I have a macro in the framework that iterates over children. You can't do that with a function easily. You can introduce iterators, but they get kind of clumsy after a while, and this is actually, I think, a clearer way of writing. And so that's one good thing. You also find them, they're also useful for, or at least I find them useful, in some cases when I'm building tabular data. There's a neat little trick that you can use where by changing the definition of a certain macro, you can make the same database of data in a text file mean two different things, or extract different information from it into two different data tables. So occasionally they're useful for formatting data. But extensive use in your code otherwise is probably unwise. So just stick to these simple things and you'll probably be all right. Now, somebody did, there was an example from Project One that I saw, and he noticed that the usual structure that's required in the Horn framework for introducing a new type of node, a subtype of node, and informing the system to use the by means of exemplars, to use the right type to create things of a certain with a certain syntactic category. So the make tree stuff. So he noticed that all of that boilerplate looks very similar. So he put in a macro. You give it, I think you give it the name of the class and maybe some other things, and it produces all of that. It produces the exemplar and all that sort of thing, and that's kind of nice. You have to be a little bit careful because the thing about a macro is that in the source text you see this one line, this macro, and if there's anything wrong in it, if anything goes wrong, and you're trying to use the debugger, you will get very little useful information because you'll be sitting right here on this line with the macro expansion, and it'll say there's a problem, and you have no idea where in the macro exactly it is. So you do have to be tasteful about that use also. But that's I think that can be a legitimate use if you don't go overboard with it. Okay, good. Let's take a break. Yes.
I have a question completely unrelated to this class.
Good.
So I noticed that you are teaching 61B in the fall, and so that'll be this is my 4th year. That'll be my kind of last semester, and I was interested in being a TA for you. I'm wondering if you accept undergraduate TAs, what the process
Yeah,
is.
that's an interesting question. We actually have undergraduate TAs in 61A. Unfortunately, the campus policies have been written in such a way as to make that difficult because make undergraduate TAs expensive because the campus does not pay does not pick up whether it's some fee or another, and the department feels obliged to supply it, right? So, nevertheless, you can always apply,
Okay.
and maybe we can. Since frankly, for 61B and 61A, I prefer undergraduates, but
How do I go about applying?
I'm not sure. But I think if you go down and talk to no, I'll look into it. I'll
Okay.
see what that is,
Thank you.
see what possibilities.
I had a quick question about refactoring. Sorry. So I had an argument with my friend about whether or not it's worthwhile to just refactor whenever a method gets a little long, like 20 lines or so.
Uh-huh.
And I was in favor of it because I said, well, the compiler will just, if it sees that one method, it's only called in one place.
That's right.
Compact that, but he said that no, because I don't know what his reason was. I guess there are too many frame pointers on the stack.
No, I mean you can. I think that if you declare, well, first of all, once a method reaches a certain length, it doesn't matter if it's inlined or not, right? Because the call overhead becomes trivial compared to the bulk of the method. So, and if you declare something to be inline, then it will be inline. If feasible anyway, it will be inline. So, no, I don't. I see there's no harm in doing it. If it improves the clarity of the program, there should be no harm in doing it.
What about Java, where you don't have that kind of thing?
Well, Java compilers these days are better. They do a certain amount of inlining. The problem, of course, is that you can't inline a virtual method unless you know that it's final. So you have to be a little bit careful how you do it. But I think some of the better just-in-time compilers can inline Java as well as anything else. Again, it depends very much on whether the method is in fact determinate.
That's the same in C++ if you have virtual methods.
That's right. But in Java, things are by default virtual, whereas in C++ they are by default non-virtual. So it's different.
Oh yeah, and the pp.exe thing works.
The which?
The whole pp.exe when I switched it to .exe.
Wait,
In the makefile,
Uh-huh.
I asked you on Monday.
yeah.
When I changed the makefile for the dependencies to have corn pp.exe.
Oh, it done exe. I thought you said exit. Okay,
Yeah,
done
exit.
exit. Yeah. I have to figure out how to what's the right way to put into the configure file. There seems to be a standard way of testing to see whether you should have exe. And it seems to consist of calling the compiler and seeing whether it produces an exe file, exe extension. And
the subversion link thing, that's just apparently a quirk of Windows. If it sees a symbolic link in the repository and you try to check it out on a Windows machine, it just says, I can't do that. I don't know.
really, well, symbolic links are a Sigwin thing.
Yeah.
They're not in Windows at all.
I use Tortoise SVN.
You use one?
I used Tortoise SVN when I
Uh-huh.
checked out the corn files. So when it saw the symbolic link, it couldn't check it out.
It didn't say anything?
It didn't tell me that. I just looked at the file and it says link test heading. So it just doesn't work with them.
Well, let's see. I suppose what I can do is to have the symbolic links created by the makefile. But I don't know if that would. I could probably do that for the sake of Windows. Okay. Yeah.
So I just had a question about the object-oriented way about doing those things. So I think we're using your skeleton, and I think you only have a handful of generalized nodes like spin-off, but you don't have add node, subtract node.
Right.
So should we create a bunch of sub-nodes for every single
Well,
type?
let's consider that particular case.
Okay.
You've got the thing about binop In fact, this is a good question. Let's ask it. Let's start things up again and ask that question generally. Okay. So, all right. Let's get started here. So a question just came up in the break, and it sounded like an interesting question. A particular example of this question of object-oriented organization. So, as you know, there is this BINOP node in our framework that is supposed to, in our ASTs, in which you provide two operands and an operator. And the question is, should that be differentiated? In other words, it doesn't make sense to differentiate that into a bunch of classes for add, subtract, and so forth. Well, that's a very interesting question, and there are a number of ways of answering. Of course, you can do that, but it occurs to me that all of those things will be extremely similar to each other, so you'll have to have a bunch of code in BINOP itself. But the other thing is that you can use another programming technique to accomplish the same sort of polymorphism, which is that you can have a table that contains, that's basically indexed, or you can have tables, I should say, that are indexed by the operator name and that tell you the various things you need to know. For example, what is the type? For example, you need to find the type of the operator. Well, you don't have to do a bunch of ifs, because what happens is that you can have I can imagine a table in which you do something like you call this thing, and it tells you, and it gives you what the type of this particular operator is supposed to be. Actually, in this particular case, however, in this particular project, it's even easier than that, because all of these operators are defined. In fact, they don't. The meaning is not really wired into the language, because all of them will have declarations of methods in the standard prelude. In other words, for the classes that you're calling. So when you apply plus to an int, it will tell you that when you do the normal method lookup, you'll get a function that has ints as its operands. So and the code that you produce, or the naive code that you produce, will be simply to call this function in the runtime, just as you would call any function. So actually, there's not really a lot of specialization that you need. Now, the trick comes when you're trying to write an optimizing compiler, or let's say a compiler that's not naive. And in this case, of course, at runtime, when you get to the runtime code, finally, which is the next segment, you're going to have to do some differentiation of plus from minus and so forth, because they have different operators and they might have different treatments. But even there, I think some sort of a pattern matching approach might well help. So we'll look a little bit at that topic when we get to runtime organization. But I think that for this particular project, you'll find that there is a uniform way of handling, a uniform operator blind way of handling the binary operators that makes it unnecessary to subtype them. That might not always be the case. Yeah.
The example that you gave of like a subscription, so we have different nodes, like those types of things?
Well, subscription at the moment has a different type of node, yes. Of course, when you implement it, you'll be able to make use of the same, if you organize things correctly, you'll be able to make use of the same machinery that is used for other kinds of function lookups, because it will eventually point to some method in the standard prelude, the __ get item __ method, right? Which is why there is that extra node that gets inserted into the thing. Okay, let's see. I was originally going to start this on Friday, and I think I'll do that after all, since we don't have enough time to get this properly going. So next time we will start we will start working on the last segment of the course, which is also known as Project 3, and that will end things up.